The title of the last of today's presentation is Reliability through Digital of Traceable Data. Guillermo Monasterios from INTI, Argentina will be the speaker. Guillermo has an engineering degree in electronics. He's in charge of the S-parameter laboratory, dependent of the Physics Metrology Department at INTI, Argentina. He's involved in different RF and microwave metrology projects at INTI and at UTN University from Buenos Aires. He has written scientific papers, given lectures and training courses in order to disseminate high-frequency related topics within our metrological community. So, good evening, Guillermo. Go ahead with your presentation, please.
Thank you, Diego. Are you looking at my presentation? Okay.
Yes, we can see it.
Okay. Hello, everyone. I'm glad to be presenting today. My name is Guillermo Monasterios. I work in the high frequency laboratory at INTI. First of all, I would like to tell you about one of the high frequency quantities we work with. For example, I would like to show you what an S parameter is and some of the complexities it has, some solutions to manage them. But I don't want to show you what we do only, but I want to give you some ideas and tools that you could adapt to your metrology work. So let's go ahead and start with some conceptual diagram of what an S parameter is. Here on the left-hand side, you see an incident wave, the green arrow, and a reflection wave of some kind of length, a transmission wave also. This is because we at high frequency work with waves, and as you see in the center of the slide, you see that you can describe each wave by two numbers, for example, a magnitude and a phase, with this phasor representation. The velocity at which this phasor rotates determines the frequency, but the frequency of the wave will be our parameter. So we are using two numbers for describing a wave. Basically, an S parameter is what impedance is at low frequency. It gives you information about mismatches in a transmission medium. And mathematically, it's a ratio of two waves. So, because a division of two complex numbers is another complex number, that leads us that an S parameter is a complex number too. Okay, but that means that it has it's a two-dimensional quantity. Okay, here we have a number example. We have well, seeing here a real and imaginary part. It's simply a different description of a point in the complex plane. You can use magnitude and phase, the same thing. Here at one specific frequency, 1 gigahertz, for example, it doesn't matter. And because due to the fact that we have two numbers, we need two different uncertainties. Okay.
Disculpa, Guillermo.
Yes.
Algunos usuarios tienen problemas para ver la pantalla. ¿Puedes dejar de presentar y volver a presentar?
Okay, no problem.
Thank you. ¿Está cerrado tu micrófono?
Sí.
Ok. And try again. Ya. Right, little.
It's okay now?
Yes. Okay.
Okay. So this is just a physics description, and I'm start from here now. So we have two measure values, two uncertainties for each of them. But the thing is that we could have a correlation between these two uncertainties. As I said before, we are measuring here at one single frequency, but not very common in high frequency. We usually trip across many frequencies, for example, to know the shape of this filter. We could use, for example, 1000 frequency point, and this particular device has 4 S parameters, right? Each one with 2 components. So as you see, we have a huge data set. And now a lot of correlations may appear. For example, we have correlations between different S parameters, between different frequencies. In addition to that, we could have correlation between different DUTs. Why it's like that? The short answer is because you are measuring different devices with the same equipment, right? This is when I'm talking about high frequency quantities, it's applied to metrology in general. Maybe if those two devices belong to different users, it's no problem. But if the user then use both devices in the same system, maybe correlation should be taken into account. So far we have a lot of data, a lot of correlations. Let me talk to you a little bit about this picture you already know, the traceability pyramid. There are 2 concepts I want to highlight here. This pyramid is replicated within, for example, one NMI in this fractal-like shape. For example, the S parameter laboratory gives traceability to the communication lab and to the EMC laboratory. And then from the communication laboratory gives traceability to the health-related equipment laboratory. And in fact, this pyramid also occurs within my own laboratory. In general, this is in the first echelon of the pyramid, because I have primary standards that give traceability to secondary standards and so on. So what we need is to flow in a bottom-up fashion the traceability through all the echelons, okay? Maintaining all the data we've seen before and its correlation. A second concept that may be not quite obvious for everyone is that the traceability point to different measurements, okay? The equipment you use here is not relevant. It has nothing to do with traceability. It's a chain of measurements, of quantities. So it's a scientific process, okay? Measurements linking different level of standards. Even though another administrative statement later promise the user that you have traceability in a certificate, the reality is that it's a scientific process, okay? I want to point out this because it gets new relevance if you want to face digital transformation. We are going to back to it later. But the way you jump from one echelon to another, to the next one, see, the way you relate one measurement to the other is through a mathematical functional relationship. For example, you have an example of one of these relationships, as could be your measurement model. There are several input quantities, and each of them is consisted of a deterministic value and a stochastic value in uncertainty. But you cannot work them together because of the different nature. You cannot simply multiply your uncertainty by your measured value. For example, if your model tells you so, because it will just make your measured result disappear, because it's assumed that your uncertainty tends to 0. But this is when the GAM guide comes handy, when it's law of propagation of uncertainty, in which suggests you to separate your calculation into deterministic values and the uncertainty propagation, right? This is why you have uncertainty budget. So at the end of the process, you join both results, and this is what you usually see when people talk about DCC, of the data field of the DCC. You put your result and you combine standard uncertainty and the expanded factor. The problem here is when your measurement model is quite complicated to calculate the partial derivatives in order to evaluate the sensitivity coefficients. Most times people create a new model, okay? Make simplifications only to be able to apply the law of propagation of uncertainty. So now you have a simplification model from a measurement model, which itself was a simplification of the physical process. Even though sometimes you cannot simplify your model to apply the law of propagation of uncertainty. So what we do in the S-parameter laboratory, and what I recommend you to do, is to use just one model and propagate uncertainty to the same model in which you propagate the result value. Is called rigorous method. This way you can manage measurement model that like the one you see at the right hand. This is the simplest model in S parameters, and it's quite complicated in there. By this, you avoid splitting your model into two different models, and it's straightforward to implement a digital transformation here. So we have only one model, no budget in a spreadsheet. But what happened with this thing about not mixing systematic and stochastic values, because this was the first problem. This is solved through what is called uncertainty numbers, or uncertainty objects, as I call them here. Uncertainty numbers are data types that describe measured quantity. Okay, it can encapsulate information about the measurement, including the measurement value and its uncertainty. They will flow together to your measurement model through all the calculations, but they will not interact between them. Here you have an example of how you can type it in a code, simply separating them by a comma. And it doesn't matter if you don't have an uncertainty at that time, or if you only want to input an uncertainty, you put the other value in 0, but you should always use an uncertainty number. So the idea is to rewrite your measurement model, but this time using uncertainty numbers. Okay, this way you can use only one model. Okay, but what happened with the complicated calculation, because it seems that things is getting worse, because now we have these strange entities. So we are going to apply automatic uncertainty propagation, so the difficulties are passed to the computer. And this is what, or the idea is what compilers do when you compile your code. The idea is to simplify your measurement model into simpler parts. Here, for example, imagine you have a remote sensor sampling electrical quantities. The goal here is to obtain a resistance and a reactance, okay, which is an impedance, right? And what we are going to do is split, okay, to break down the original equation into simple parts. For example, the first thing I want to do is make the division between voltage and current, and I will save in the first step, where it says y1, the partial derivative with respect to the voltage and the current. Okay, this is because we are still applying the law of propagation of uncertainty. Okay, even if I'm not using a different uncertainty mode. The same thing with other variables. How we split this equation is because I know, or the computer knows, how to derive a division. They know how to derive a trigonometric function. In the second step, you see, likewise, we have that the resistance will save in a digital file. This is where, or this is the logic. The resistance we have the partial derivatives with respect to y1 and with respect to y2. And by way of the chain rule, we have the partial derivatives at the output variable with respect to voltage and with respect to the current, even though we are managing only simple algebraic operation, right? It doesn't matter how big or complicated was your measurement model at the beginning. Okay, so here is highlighted the independent variables, the dependent variables, and in addition to resaving the partial derivatives, we are going to save the dependencies. So I know that the resistance depends on the voltage, the current, and the phase. Okay, so all this information will be stored in a digital file, and with this information I could restore all the uncertainties and correlations I've mentioned before. This pyramid on the left side is just to remember me to tell you that recall one of the concepts we were talking before about traceability. This way of working let us have the whole traceability chain explicitly write it in a digital file. Okay, maybe the output here, the resistance and the reactance, could pass to another laboratory, and they will become the input quantities to a new calculation, and become intermediate variables, and so on. So this concept could be translated into, or just passed to different laboratories. Okay. At the bottom left, you have what an uncertainty number has, at least one of its implementations. This implementation was done by the NMI of Switzerland, META, and you have the measurement value, the dependencies, and the partial derivatives. You have not uncertainties here, nor correlations, but you can obtain on real time, so to speak, on demand, your derivatives, your uncertainties, just multiplying your partial derivatives by the values of the input quantities. They are already known. Going or walking through this tree shape in the reverse order, because you have all the dependencies, you can calculate the correlations you want to ask to the code on demand. Okay, so this is the only thing you know to know about your measurement. If you are going to perform a type A uncertainty evaluation, well, the degree of freedom will be taken into account. So here is how it looks like. An uncertainty number. You see, I read out the VNA. VNA is short for Vector Network Analyzer. Is what we use to measure S parameters. So this is the general fields. You have a real part and imaginary part. You see now here that you have dependencies to an input quantity, an influence quantity, and a Jacobian, which is a term from multivariable statistics, but it's the partial derivatives. The same, of course, with the imaginary part, and all of this is for each frequency. Okay, this is how an XML file looks like. This is generated automatically. You see that between the frequency tags, you see the real and imaginary part. There are 4 pairs of that. I don't know if my mouse is like this. 1, 2, 3, and 4, because this is an XML file. For example, for the bandpass filter we've seen before. If we expand the real tag, we see the measurement value and different dependencies. Okay, when it says depends on, okay, the depends and its correspondent partial derivative of each Jacobian. Okay. Once we have this XML file, all the measurement process is already there. The DNA of the measurement is there. It doesn't matter if we are talking about higher frequencies or in metrological area. It's the same concept. There is another implementation in where you have actually the uncertainties and correlations explicitly written in the uncertainty number. This another implementation was done by MSA, the NMI from New Zealand, and was developed by Blair Hall. But you already done. You can ask for write commands to interact with this XML file and get, for example, going through this tree that we've seen before, the correlation, for example, between real and imaginary parts within one S parameter, or between different S parameters, or at different frequencies. This is all generated just within this XML file, this tree flowchart. We can draw our measurement values and magnitude and phase. We cannot look at this. These uncertainty errors are not just an offset superimposed to the median values point to point. They are being calculated on real time, taking into account the correlations. Okay, and you see the same here. These are the coverage areas, coverage the coverage areas for a two-dimensional quantity at different frequencies. That's why you see different surface here. Okay, the reality is that you don't have an uncertainty budget now, because we are not using a spreadsheet and Excel uncertainty evaluation. So if a reviewer asks you for your Excel budget, well, you're going to say, I don't have it. But before the non-conformity, you just type budget command and it's going to pop up. And you see the budget is generated automatically, recurring this, walking through this three concept. Maybe some of you have a quite complicated measurement model. All the algebraic operations are overchecked. So, for example, I'm using here an inverse fast Fourier transform, and we are still doing or propagating uncertainty using this uncertainty object. Okay, just a reflection. For me, this thing about digital transformation doesn't start with the DCC. It started from, it's my opinion, okay, with another instrument became an embedded computer. And for example, the DNA you see at the right hand, it's a Keysight DNA, and nowadays it's showing you uncertainty bars, but they are not taken from specification. They are actually calculated in the same way we just seen on real time. Okay, the same happen with software from Maury Microwave or DNAs from Rode Schwarz. All of them have options to calculate uncertainty, propagating in different steps with automatic differentiation. Here is a code written with GTC. This is short form GAM3 calculator, the software made by Blair Hall of New Zealand. It's straightforward. We have an extra complexity because the input quantities have correlation from the beginning. This is an example of what we've seen before about the electrical quantities. This is actually an example from the appendix H from the GAM. Here I want to note that if you already have your measurement automatic, I mean the result, the measurement result, now what we are doing is to automatize the uncertainty propagation. So at the end, you have all your process automated. We are finishing. This is how we give our certificate to our customers. The XML file is compressed because we have a lot of data and its size could be very large. So these zip XML are attached to a PDF certificate. In this PDF goes written a checksum of this digital file, because the customer later will extract the data files. We want to have some kind of linking that to ensure that the data will not be modified. And this PDF, with the attached XML, are digital signed and send it to the customer by email. The user next, the only thing that has to do is to import this or extract the digital file, import it to his automated controller system, and without type any number or anything, they could start making measurements with traceability to INTI. Well, I think this is what you want to know. The libraries that make all the magic are the unglib, written by Michael Gollensack from Metas, and they hold the packages in CTC. Both are free, not the commercial options, but these are free. You could use unglib from Python, MATLAB, or C#, the GTC from Python. The best suggestion I can do, can offer to you, is to download them, try them. I guarantee you that your expertise will speed up, will increase, because you could compare what your Excel's calculation offer you against these libraries, and a lot of questions will arise, and you will be able to answer them, or answer questions that maybe before were prohibited because of the practical implementation of this test. Okay, I hope this presentation has been useful to you. Feel free to ask questions. Thank you.
Thank you, Guillermo, for your presentation. And let's see if there are some questions in the chat. So the first question from Ruben Gil from Inacal is, how is a certificate handed out to the client?
Well, I think I show you, and
yes, I think his way to say that it's, if you send an email, or you land a CD, or how it's or a blockchain, or how is this handed out?
Yes,
and what is yes, it's megas, bytes, or gigabytes, all the capacity of the information you are sending. Yes.
If you don't compress the XML file, two-port device, which has 4S parameters, could have a size of 200 megabytes. That's why it's compressed. This reduces its size to around 20 megabytes. It's sent by email. We didn't have any request to encrypt the data so far. But yes, by email.
Okay. Okay. The second question is from Francisco Flamenco from Senam. Is this about the digitalized? This is a digitalized certificate. Have you made a comparison about the creation to verify the structures?
So the structures of
the XML, I think. if you are making the same analysis or the same XML of the metas and the NSSLI of with the blur hole main method, if you are all doing the same method.
Yes, actually, the libraries itself generate the XML file.
Yes.
You don't need to replicate the structure. So when you save your output quantities or your intermediate, in addition to your output quantities, when you save that object, the structure are automatically generated. So there will be no difference between different institutes using the same libraries. Just to point out that the CTC, the GAM3 calculator, save a JSON file, not an XML file, and the metas use an XML file.
XML file. Okay. So we don't have any more questions. So thank you very much, Guillermo, and for answering all the questions.